Okay, so welcome back to another video. So here we have a definite integral from 0 to 1/2 of ln square of 1 minus x divided by x dx. So solving this along the way, there's actually going to appear two special functions, the dilogarithm and the trilogarithm. And also along the way that when we're doing such calculations, we're going to get some special values that we'll be utilizing as well that's going to be treated as given that for such the trilogarithm and the dilogarithm functions. So it's straightforward to see that we're going to be using a bunch of calculus techniques. I think you can see the first step rather, is that we're actually going to be utilizing a u-substitution and some other, as I said, other calculus techniques that regarding with the integration by parts as well. So expect to see a bunch of those, but of course, mainly the dilogarithm and the trilogarithm function is the big key to solving this. So other than that, let's actually just jump straight ahead. So I'll let this be called capital I. And so as mentioned, our u substitution we'll start off with is we'll let u equals 1 minus x. So of course I have an x on the bottom, so I'll have to solve x by itself to get that substitution as we convert this into terms of u. So that means x is equal to 1 minus u. So if I just differentiate this both sides, so that means dx is equal to negative du. And performing such substitutions, and of course we have to calculate our new bounds. If I plug 0, this is going to be 1. If I plug 1/2, this will be 1/2 on the top. Then I'll have ln square of u, then divided by 1 subtract u, then of course with the negative du differential for the substitution of the dx. So of course we need to flip our bounds because we have 1/2 and then 1 from both the top and bounds. So of course we just switch that up and then that becomes negative, but that also cancels out that negative as well. So I have 1/2 to 1 ln square of u divided by 1 minus u, and then left with just du. As mentioned again, that we'll be actually utilizing some integration by parts, as you can tell from here, that now we can actually need to choose which function will be u and then which function will be our dv. So the easier function we'll be using is that we'll suppose that I'll actually call this variable w since we have a u. So we'll let w equals ln square of u. Then if I just differentiate both sides, so that means that's going to be dw is equal to 2 times ln of u divided by u and then du. So next is to choose our dv substitution. So we're actually going to let this be 1 divided by 1 minus u and then du. So if I just integrate that both sides, so of course we have our v is going to equal negative ln of 1 minus u. So now we just put this back together to get our new simplified I. So I now is equal to, so plug w times v, so that'll give us negative ln square of u multiply with ln of 1 subtract u, and then we evaluate for our bounds from 1/2 to 1. Then subtract, but also don't forget that I have a negative over here, so I'll factor that out, and so that'll become a positive. There's a 2 over here, so I'll factor out that constant. So we have 2 times the integral from 1/2 to 1 of ln of u multiplied with ln of 1 subtract u, all this being divided by u, then du. So let's start off with one thing at a time and let's calculate our bounds. So if you see that if I calculate this at 1 ln square of 1 is going to be 0, then I have an ln of 1 minus 1, ln of 0 is undefined. So being that the case, we would have to write this in terms as a limit, then convert that into the form of a rational form such that as you take that limit, you will also get some indeterminate form, eventually yielding you to use L'Hopital's rule to eventually, that way we can actually say that this whole thing approaches 0 when evaluated at 1. So now what's left is let's plug in the 1/2. So I have ln square of half and then times ln of 1 minus 1/2, which is still 1/2. Combine that together, that's a ln cube of 1/2. In other words, that if I convert the negative, since it's a subtraction, that'll become a positive, but we can actually apply logarithm rules, so that's the same thing as ln of 1 subtract ln of 2, so ln of 1 is 0, distribute back the negative, and so therefore we're just back to the negative again. So negative ln cube of 2 will be our value there, and then just continue on with the 2 times the integral of 1/2 to 1 of ln of u times ln of 1 subtract u divided by u, and then multiply with du. Going from here, so now let's actually, now we're going to be utilizing the dilogarithm function. So let me actually write down its definition representation. So what that represents is that Li with order 2 of x is going to equal to the negative of the integral from 0 to x of ln of 1 minus t and then divided by t dt. Okay, doesn't sound like much, but let's actually go a little one step further ahead and take the derivative of the dilogarithm. So that would have to mean that dx of the dilogarithm at order 2, or well, it's just the dilogarithm of x rather, then simply just apply the fundamental theorem of calculus over here and plug in the x and take the derivative, which is just 1, and so we're just left with that. This is going to be negative ln of 1 minus x and then divided by x. Why is that useful? Well, you can see that we have to now calculate this integral over here, which is left. So the integral from 1/2 to 1 of ln of u times ln of 1 minus u, then divided by u du. As you can see that we'll have to apply integration by parts again, so we now have to choose our w in this situation yet again because we have a u and our v, or rather our dv. So the smart choice to use for our w term or w substitution is we'll let w equals ln of u. So differentiate this, so dw is going to equal to just 1 over u, then du. Now to choose our dv, so dv will let that be ln of 1 minus u and then divided by u. And so our v in this case is, good thing we actually did the integral because it's that same representation over here, is therefore going to be the negative dilogarithm function. So negative li order 2 of u. Now we just have to plug this back in together. So now this will yield us, so negative ln of u multiply with the dilogarithm of order 2 at the variable u, then evaluate this from 1 to 1/2, and now just put in the integral. So I factor out the negative coming from here, so this is from 1/2 to 1 of just the dilogarithm of u and then divided by u du. Okay, so now let's plug in our, let's evaluate our terms. Plug in 1, so ln of 1, that's going to be 0, so that's fine. But if you're curious to know what li2 of 1 is equal to, that's actually going to be pi squared divided by 6. So what's left is just plug in the 1/2 bound. So ln of 1/2 and then the dilogarithm of 1/2. I don't know why I keep saying li, I like to read letters. That's just coming from my personal stance. So of course, doing so, apply the logarithm log property, so I now have ln of 2 after that simplification, and so we're just going to keep the dilogarithm evaluated at 1/2 the way it is at the moment until further notice. So with that, then we're just going to keep the same thing over here for this function over here, well, integral rather, so 1/2 to 1 of the dilogarithm of u and then divided by u du. So now that means that with this integral calculated, now we can actually write a new simplified form of I. So we just have to distribute, well, rather not distribute, but rather substitute the evaluated integral for here. So applying this, so that means I'll have negative ln cubed of 2 minus 2 ln of 2 times the dilogarithm at 1/2. And I'm going to write the next line just to utilize some room later. And then add this with 2 times the integral from 0 to 1/2 of the dilogarithm at u and then divided by u du. And so lastly, we'll need the trilogarithm function, which is written as the following integral representation. So it'll be from 0 to x of the dilogarithm of u and then divided by u du. So what's great is that now if I just take the derivative of this trilogarithm, so basically just apply the fundamental theorem of calculus yet again, so that means this is just the derivative, this is 1, then plug into x, so that means I have the dilogarithm of x divided by x. Okay, and so now we can actually now just easily calculate this integral over here. So now the integral from 1/2 to 1 of the dilogarithm of x, or rather, now we're still in the term, and we're still in the world of u. So u and then divided by u du, which is then just equal to the trilogarithm of u. Then evaluate this from 1 to 1/2. Then it's gonna, of course, gonna come with its special value. So we're gonna leave that as 1 and then subtract li3 of 1/2. Here are these special values we'll be using. We're gonna treat these as given. So I have the dilogarithm at 1/2. This is going to equal to pi squared divided by 12. Subtract ln square of 2 divided by 2. Next one we have is our trilogarithm evaluated at 1. So that representation is easy to see that this is actually going to be equal to Riemann zeta of 3 using that summation definition. And so this last identity is going to be a pretty long one. So the dilogarithm of 1/2 is going to be evaluated as 7, the Riemann zeta of 3 divided by 8 minus pi squared times ln of 2 divided by 12, and then add this with ln cubed of 2 divided by 6. So now putting all this, we now have the negative ln cubed of 2, then minus 2 ln of 2 multiplied by the dilogarithm evaluated at 1/2. Add this with 2 times the trilogarithm evaluated at 1, and then subtract 2 times the trilogarithm at 1/2. Okay, and so if you just plug these identities, everything together, and substitute that in, I'll leave the verification for you guys to save the work. It'll reduce down to the following final results. So we have the Riemann zeta of 3 divided by 4, then subtract ln square or ln cube of 2 divided by 3. And it's just like that. That is indeed our final result to our given integral. So of course, we're using both the dilogarithm and the trilogarithm functions with, of course, the special identities that came in handy with this process. So yeah, that's pretty cool if you ask me.